Chapter 16, Chemical Reactions, which is one of my favorite chapters because we start really concentrating on combustion and the fuels associated with. So fuel, any material that can be burned to release thermal energy. So if you can burn it, it releases thermal energy, we're calling it a fuel. Most familiar fuels consist primarily of hydrogen and carbon, and they are also called hydrocarbon fuels, right? So CNHM is what it's denoted by, the general formula there. And you can see crude oil, it going from crude oil being heated up to gasoline, kerosene, diesel fuel, and fuel oil. So those are the byproducts that we can make from heating up the crude oil. Hydrogen carbon fuels exist in all phases. Some examples being coal, gasoline, usually treated as octane, and natural gas. So you can do a solid, right, a liquid, and a vapor. Okay. Oh, and this is the distillation process of it. That's how we get the liquid carbon fuels that I just listed. It's from a distillation, so that's where we get those. This is a comparison of some alternative fuels to the traditional petroleum-based fuels used in transportation. And here they are. You've got gasoline, diesel, heavy diesel, LPG, so it's liquefied petroleum gas. It's propane, ethanol, methanol, CNG, and LNG. And here's the energy content there. So you see how those are different, and they differ pretty drastically with some of them. And then the gasoline equivalent. So here, when we're talking about fuels and combustion, it says the oxidizer most often used in combustion processes is air. Why? Well, there's a couple of different reasons. Obviously, air is readily available. It's all around. You need an oxidizer, so you can definitely use oxygen. When we're talking about just fuels and combustion, in particular, you need, so combustion here is defined as a chemical reaction during which a fuel is oxidized and a large quantity of energy is released. So we can look at the fire triangle. So right here, these are the three things that you need for a fire and to get that reaction. So of course, first you need an oxidizer, right here. Oxidizer. So most often, this is oxygen. It's readily available. It's free. It exists. You don't have to do anything for it to be there. And the only caveat to that is if you do have a situation like you are maybe in a vacuum, and it doesn't have any, or something is happening within a vacuum and it doesn't have any air. Maybe you can't have air for this certain reaction. Then you can use some other form of an oxidizer, but it's very rare. 9 times out of 10, even more than that, you're going to use air. Okay, and then you also need some type of fuel. And this can be anything. It can be wood, it can be paper, it can be coal, it can be oil, anything as your working material that is going to carry the flame. Let me write in here, this is a fire triangle. Okay. And then over here, the last thing that we need is we need some form of heat. And so most of the time, it's by way of an existing fire or a spark, really is where it comes. Because even if you think, oh, well, a lighter or matches or something like that, you can even see the spark happening from friction. So you need some sort of heat, and it's typically by way of a spark. And here, our fuel for combustion is typically some form of distilled crude oil. But back to that heat, you can do You can do a spark. You can do an existing flame. You can even do, you know, when you were a kid, you saw the magnifying glass and you probably tried it and maybe failed miserably like I did. Tried to use the magnifying glass with the sun to try and start a fire when I was a little kid. Or, you know, rubbing two things together for friction to create a spark. So these are the things that you have to start a fire. Okay. And so then a big part of that obviously is the oxidizer. And we typically use air because it's just readily available. It works well. And you don't have to do anything else to it. It just needs to exist. A fuel must be brought above its ignition temperature to start the combustion. So when we go back to this fire triangle, these things need to happen all together simultaneously. So you need a spark while you have oxygen, while you have some sort of fuel. This fuel will not ignite unless you bring it above its temperature. So if it's a really cold day and you're trying to start a fire, you're going to need more heat to elevate that fuel to its ignition temperature, and then it can start to combust. Okay? That's why wildfires, like in the forests and stuff like that, they spread more quickly and they're much more dangerous. I mean, they're very dangerous anyway, but they're much more dangerous in the summer and in dry areas because the temperature between the ignition temperature and it just existing, or the environment temperature, is much smaller than when it's in the dead of winter, you know, or if it's covered with snow, right? So you need to bring a fuel to its ignition temperature and above for it to start to combust and maintain that combustion. The minimum ignition temperatures in the atmospheric air are approximately, and it's different for each one, 260 for gasoline, 400 for carbon, 580 for hydrogen, 610 for carbon monoxide, and then 630 for methane. This is really important to note that the lowest one here listed is gasoline, which is really nice when you're thinking about cars and how readily available they are. You don't have to bring those up to such an extreme temperature. I mean, it's a very high temperature anyway, but could you imagine having to bring it up 3 times that amount if your vehicle ran on methane, right? Proportions of the fuel and air must be in proper range for the combustion to begin. So you have to bring them up to temperature for them to begin. For example, natural gas does not burn in air in concentrations less than 5% or greater than 15%. So you have to have them in the correct ranges for it to start to burn. Too much is not right, and too little is not right. So you have the 2 reactions coming in. What you typically see, this is similar to a fire triangle here. So remember, we needed a fuel, you needed some sort of heat, and you needed, we'll just write air because it's short, but you need some sort of an oxidizer. So into here, you can have the oxidizer, and in here, you can have the fuel. And then here, this reaction chamber, you could have some sort of spark here. And then out comes that product. In a steady flow combustion process, the components that enter the reaction chamber are called the reactants, and the components that exit are called the products. So the reactants enter, the reaction happens, and then product is produced from that reaction. The total number of moles is not conserved during a chemical reaction. So, sorry about that. The mass of the number of atoms of each element is conserved during the chemical reaction. So moles are not conserved, but mass is. Air-fuel ratio, AF, the ratio of mass of air to the mass of fuel for a combustion process. So this is just so that you have the right amount, right? You don't want to, if you start dumping in so much air and a little bit of fuel, you won't really get anything, and vice versa. Fuel to air ratio, FA, is just the reciprocal. M equals NM, mass, number of moles, molar mass. So that's just, we've been looking at that. Okay, and then here is the combustion chamber again with 1 kilogram going in of fuel, 17 of air, which happens, the air-fuel ratio is then 17, and then the product is 18. Okay, and then when you have the air-fuel ratio represents the amount of air per unit mass of fuel during the combustion process. So it's important to know that what you have over here, right, it's the ratio of mass of air, 17, over the fuel, which is going to give you an AF of 17. But then when you have the product, those are added. Okay, so that's how we get those. This one right here is a ratio. This is air over fuel. And then this is air plus fuel. So here's an example. It's just balancing the combustion equation. Here's one that you can walk through if you'd like. This just lets you know what you have here, and then plugging them into equations. Complete combustion. If all the carbon in the fuel burns to CO2, all the hydrogen burns to HO2, and all the sulfur, if any, burns to SO2. Incomplete combustion is the combustion products contain an unburned fuel or component, such as C and then H2, or CO or OH. So you see how those are not as complete as above. What are some of the reasons for incomplete combustion? Well, it goes back to those ratios: insufficient oxygen, insufficient mixing, dissociation, which is high temperatures. Oxygen has a much greater tendency to combine with hydrogen than it does with carbon. Therefore, the hydrogen in the fuel normally burns to completion, forming HO2. So here we have a combustion process that is complete if all the combustible components of the fuel are burned to completion. So this is just showing it burning to completion. It's theoretical. Stoichiometric and theoretical air, the minimum amount of air needed to complete combustion of a fuel, also referred to as chemically correct amounts of air, and therefore 100% theoretical air. Stoichiometric and theoretical combustion, the ideal combustion process during which fuel is burned completely with theoretical air. So when you take this and plug it into the combustion, then you have the ideal combustion process. And then excess air, the amount of air in excess of the stoichiometric amount, usually expressed in terms of stoichiometric air as percent excess air or percent theoretical air. Deficiency of air is just the amounts of air less than the stoichiometric amount, and it's expressed as a percent deficiency of air, and then just the equivalency ratio. So the comparing of those two is the ratio of the actual fuel-air ratio to the stoichiometric fuel-air ratio. And so here, so 50% excess air is 150% theoretical air. 200 excess air is 300 theoretical air. 90 theoretical air is 10% deficiency air, because remember, all of it's 100% when we're talking about theoretical or ideal. So if you have excess air, you're just adding it to this 100. If you have excess air, you're just adding it to the 100 of theoretical. And if you have 100 theoretical air, but you are only calculating 90, well, then you have 10% deficiency air, because you should have 100. The complete combustion process with no free oxygen in the products is called theoretical combustion. So that's saying that we've used everything. There's no free oxygen in the things. There's no unburned fuel. everything is complete. It's the complete combustion process. It's theoretical combustion. Predicting the composition of the products is relatively easy when the combustion process is assumed to be complete. And that's because you can consume the max limits of everything, right? With actual combustion process, it is impossible to predict the composition of the products on the basis of mass balance alone. Then the only alternative we have is to measure the amounts of the component in the products directly. So this is where we talked about mixtures. Now we're trying to get into, because you see the fire triangle, you have 3 different things, right? 1, 2, and 3. So obviously it's a mixture. And here you're going to have multiple components in the mixture. So we need to be able to measure the components directly so that we can then start looking at what this actual combustion process is. A commonly used device to analyze the composition of combustion gases is called the ORSAT gas analyzer, and the results are reported on a dry basis. Okay? And so here you have just a before and an after. And this is determining the mole fraction of CO2 in combustion gases by using the ORSAT gas analyzer. So if we're not going to look at any changes in KE and PE, the energy change in a system during a chemical reaction is due to the change in state and a change in chemical composition. So the first part of the semester, we looked at KE, PE, total energy, things like that, energy of a system, right? We looked at all of those things. Well, now if we negate all of that, we're going down one step further, one step deeper, and we're looking at it on a chemical level and the state changes within those chemical compositions. And this is where we get into moles, right? And the latent energy in between those two. The microscopic form of energy of a substance consists of sensible, latent, chemical, and nuclear energies. We briefly talked about that, but not too much. And then when the existing chemical bonds are destroyed and new ones are formed, so it's being changed on a molecular level, right? So remember when we were talking about a book, and we're holding it and we drop it, and that kinetic energy changes to potential energy, right? The chemical makeup of the book is not changing. It's just the energy that's being stored. It's just transferring. But when the existing chemical bonds are being destroyed, like in a combustion, right? When you are actually changing the form of these mixtures, when the existing chemical bonds are destroyed, and then new ones are formed because it's changing molecular makeup. Usually a large amount of sensible energy is absorbed or released. Okay? The enthalpy of a reaction, so Hg, is the difference between the enthalpy of the products at a specified state and the enthalpy of the reaction at the same state for a complete reaction. So everything else staying the same, it's the comparison between the products and the reactants. The enthalpy of combustion, which is HC, is the enthalpy of a reaction for combustion processes. It represents the amount of heat released during a steady flow combustion process when 1 kilomole or 1 kilogram of fuel is burned completely at a specified temperature or pressure. Enthalpy of formation, HF, is the amount of energy absorbed or released as the component is formed from its stable elements during a steady flow process at a specified state. So we're talking about what is formed from stable elements during that steady flow process and at a specified state. So to establish a starting point, right, so that we can build off of those states, we assign the enthalpy of formation of all stable elements, O2, N2, H2, and C, a value of 0 at the standard reference state of 25 degrees Celsius and 1 atmospheric pressure. So that's where we get our starting point, And then we can start looking at those states and looking at a steady flow process and trying to find that enthalpy at formation, right? And then comparing those two states for the reactants versus the products to get the enthalpy of reaction. And then looking at what is released during that steady flow combustion process when 1 kilomole, 1 kilogram of fuel is burned completely and at a specified temperature and pressure. And then we can look at, well, what is that enthalpy of combustion? This is continuing on with a schematic showing the formation of CO2 during a steady flow combustion process at 25 degrees Celsius and 1 atmospheric pressure. So here, the enthalpy of the combustion represents the amount of energy released as a fuel is burned during a steady flow process at a specified state. And then the enthalpy formation, the enthalpy of a substance at a specified state due to its chemical composition, the enthalpy of formation of a compound represents the amount of energy absorbed or released as the component is formed from its stable elements during a steady flow process at a specified state. So here you will get a negative sign, and this is due to the fact that the enthalpy of 1 kilomole of CO2 at 25 degrees Celsius and 1 atmospheric pressure is 393,520 kilojoules, less than the enthalpy of 1 kilomole of Celsius at 1 kilomole of O2 at the same state. So it's the difference, right? So it's not taking it from a zero, an absolute zero. In other words, 393,520 kilojoules of chemical energy is released, leaving the system as heat when C and O2 combine. So remember, when it's leaving it, it's comparing. It's not like a calculating on a number line situation. Therefore, a negative enthalpy of formation of a compound indicates that heat is released during the formation. So if it would be positive, it would be heat absorbed. So heating value, it's the amount of heat released when a fuel is burned completely in a steady flow process and the products are returned to the state of the reactants. The heating value of the fuel is equal to the absorbed value of enthalpy of combustion fuel. So a high heat value, HHV, is when HO2 in the products is in liquid form. A low heat value, HLV, is when the HO2 in the products is in a vapor. So liquid for high heat, vapor for low heat. Okay? And then you have that there with the units. And for fuels with variable composition, that is coal, natural gas, fuel oil, the heating value may be determined by burning them directly in a bomb calorimeter. So that's a measuring device that we would get where we can determine the heat value. So the higher heat value of the fuel is equal to the sum of the lower heat values of a fuel and the latent heat of vaporization in the H2O in the products. The energy balance, which is the first law, relations developed in Chapter 4 and 5 that we went over are applicable to both reacting and non-reacting systems. Remember, because we have to check those boxes. We have to check the first law and the second law. They both have to check the box. We rewrite the energy balance relations, including the changes in chemical energy. So now we're taking that energy balance and we're including the chemical energies as well. So here's a steady flow. When changes in kinetic and potential energies are negligible, the steady flow energy balance for a chemically reacting steady flow system is just En is equal to E out, and that's for the steady flow. The enthalpy of the chemical component at a specified state is the sum of the enthalpy of the components at 25 degrees Celsius, 1 atmospheric pressure. So remember, that's our starting point. And the sensible enthalpy of the component relative to 25 degrees Celsius, 1 atmospheric pressure. And so here's some more, again, some equations here that is directly implementing that first law analysis. If the enthalpy of the combustion of a particular reaction is available, well, then you could use this Qn, this heat transfer, net heat transfer in, plus net work in. Most steady flow combustion processes do not involve any work interactions, right? Because we're talking about working liquids here. So most of them don't involve any of the devices that would do work interactions. Also, combustion chamber normally involves heat output, but no heat input. Okay, and so that's because, let's look at a piston. Okay, oops, where did it go? Okay, let's look at this piston right here. And this is not going to be a super accurate drawing of one, but it is going to be somewhat accurate in the dynamic of it. So you have an inlet. Let's just draw an in here. In and an out. And so oxygen, really actually two ends, because you'll have, let's just do in. So we have oxygen, and then we have the fuel, and then you have like a little spark right here. Let's just draw a spark like that. And then the out is going to be that product, right? So when you are having a combustion, like a firing order, and so in a V8, and if you've seen the inside of an engine block, they call it a V, and if you have 8 or a V4, then you'll have each cylinder, right? So each one of these is a cylinder. Okay, and so this could be 1, 2, 3, 4, or some of them, they are all lined up on one. Anyway, and these alternate, right? So the piston is right here. I should really just find a video and post it because it's going to be way better than my drawing. And this piston right here is what is in here, okay? And so if you have a V8, you're going to have 4 of these V's, and you're going to have 8 cylinders, okay? So here we're just going to do a 4-cylinder here. And so when in each one of these, you have an in and an out. And so these are going to be cycling through the shaft. It's going to be pushing the rod up and down and up and down and up and down. And so what happens is you have fuel and air come in. And so when it's exiting, when the piston is pulling out, it's pulling, when it's expanding, it's going to be pulling in oxygen and fuel in the right ratio. And then it's going to compress it. And then as it's compressing it, once it gets to the compression peak, the spark is going to ignite. And that explosion, that combustion right there is going to push this piston into another expansion. And then when it comes back up to compress it, it's going to push out the product, the vapor. And it's going to do it over and over and over and over again because this is a cyclic motion. So for closed system, the general closed system energy balance relation can be expressed for a stationary chemically reacting closed system. And here's that information. Energy in less energy out is the total change in the energy system. Utilizing the definition of enthalpy, the PV terms are negligible for solids and liquids and can be replaced by RUT for gases that behave as ideal gases. So an expression for the internal energy of a chemical component in the terms of enthalpy is just this U equals H minus PV, and then that's broken down. So in the limiting case of no heat loss in the surroundings, which is heat transfer is equal to 0, the temperature of the products reach a maximum, which is called the adiabatic flame, or the adiabatic combustion temperature. So what is that? That's when the temperature of the products reach a maximum. And this is taking into account no heat loss. This is taking into account no heat loss to the surroundings. The determination of the adiabatic flame temperature by hand requires the use of an iterative technique. The determination of the adiabatic flame temperature by hand requires the use of an iterative technique. So here, the temperature of a combustion chamber becomes maximum when the combustion is complete and no heat loss, which is how we use this insulation, is so that we can get Q equal to 0. Okay? And so the adiabatic flame temperature of a fuel depends on the state of the reactants, of course, the degree of the completion, because if you have a lot that's not being completely burned in the reaction, then we're not going to reach the max temperature, and the amount of air used, because those are all ratios, right? So you may have incomplete combustion, dissociation, heat loss, things like that. So the adiabatic flame temperature attains its maximum value when complete combustion occurs with the theoretical amount of air. It's the ideal situation. Okay? Entropy change for reacting systems. This is the entropy balance. So S in less S out plus S generated equals the change in the system entropy. Entropy balance for a system, including the reacting systems undergoing any process. And then for a closed system, reaching system, this is just the sum. And then for adiabatic processes, remember adiabatic is heat transfer is equal to 0. Okay? So here's some more information about the formulas. But when evaluating the entropy of a component of an ideal gas mixture, we should use the temperature and partial pressure of the component. Remember, so when we have a mixture, an ideal gas mixture, we just talked about this in the last chapter. When we have an ideal gas mixture, we need to use it on a component level, not on the mixture level. And we know that these are heavily temperature dependent. So we're going to use the temperature and then the partial pressure. Okay. The absolute entropy values are listed in table A18 through A25. That's what we've been using for various ideal gases at the specified temperature and partial pressure of 1 atmospheric pressure. Here it is. Plotted on a TS diagram. Okay. And at a specified temperature, the absolute entropy of an ideal gas at pressure other than PO equals 1 atmospheric pressure, and you can get that by subtracting. So we have exergy destroyed equals TOS generator, and this is just the exergy destruction. And remember, exergy is just the available energy, right? The available potential work that we could be doing. The reversible work of a steady flow combustion process that involves heat transfer with only surroundings at T0. And so this is work reversible right here. And then it's when both reactants and the products are at T0, and this is just the Gibbs function. So there's just more formulas and a reminder of what exergy is. The difference between the exergy of the reactants and the products during a chemical reaction is the reversible work associated with the reaction. So the difference between the exergy of the reactants and the products during a chemical reaction. So we've got reactants and products plotted in reference to exergy, right? So this difference right here, this is your reversible work, right here. And that's at a given state. So remember, we're staying at the same state when we're comparing these to this. Because so this could be state 2, this could be state 1, this could be state 3. We're not going to compare these, right? We're not going to compare here from state 1 and state 3. We're going to use the same state. And then here for the second law analysis of reacting systems, Of course, for this very special case, which thermodynamics is filled with very special cases, all this is saying is that we can conclude from the above equation that the negative of the Gibbs function of a compound represents the reversible work. So it's saying that, hey, for this case, we can conclude that the negative of the Gibbs function of formation of a compound represents the reversible work associated with the formation that the compound from its stable elements. So not too super additive here, but another very special case. Okay, so what we did is we went over fuels and combustion. We talked about the fire triangle. You'll want to know that. And then the theoretical and actual combustion processes. And then the enthalpy of formation and enthalpy of combustion. First law analysis, because of course we need to check both of those boxes, right? Adiabatic flame temperature, that's the max. Remember? Oops. It's the max. What is happening? This is not writing. Well, I can't write it on here. It's the max when Q is equal to 0, right? And then entropy change with reacting systems, and the second law analysis for reacting systems.